ruptures, it breaks, and it has to fill that hole that has broken. And it's actually a pretty complicated and quite elegant process that has 3 main steps. So look at that. This is a blood vessel. You can sort of see I've drawn 3 layers in here. Pardon my crappy art. This is our inside layer. Here's our lumen, and our inside layer, that layer of endothelial cells, that's the tunica intima, the tunica media just outside that full of muscle, and the tunica externa on the outside, primarily collagen connecting this blood vessel to its surrounding area. In the event of an injury to the blood vessel, what's going to happen? It's going to break. A big part of our blood vessel is ruptured. I'm going to make this a little bigger just so I can doodle in there a little bit more. That's no good. Right away, these endothelial cells around the site of the break are going to start making and secreting several different things, including, but not limited to, serotonin, which is a neurotransmitter, we've seen that before, a protein called von Willebrand factor, and another guy who we'll get to later on. So, we're secreting all of these. Actually, I'll go ahead and put the name up right now just so I can put the green away. This is tissue factor, or TF. So all 3 of these things are being secreted by these endothelial cells now out into this area. And each one of these things is going to cause a different response. We're going to look first at serotonin. This is going to trigger the first step in hemostasis. In this picture, I'm just going to go ahead and say the blood is flowing this direction through a blood vessel. Remember, we always have one-way flow through a blood vessel. Serotonin is being secreted, and serotonin is going to act on the smooth muscle here inside the tunica media, that middle layer. A lot of smooth muscle there. That's the layer responsible for vasoconstriction and vasocontraction, or vasodilation rather, I'm sorry. So serotonin is going to act on those muscles. What's going to happen, it's going to cause these muscles to clamp, maybe even on this side, some serotonin will make it down there. The whole blood vessel will contract, get smaller in size. We're going to call that vascular spasm. Why is vascular spasm important? Well, we're losing blood. Blood is flowing through this blood vessel, and now it's able to go not just this direction, but also this direction. A lot of blood is leaving our blood vessel, entering the surrounding area, or broken all the way through the skin, exiting the body entirely. Both of those are bad. We want that to stop. So if we squeeze the blood vessel here, we're going to limit the amount of blood that can flow through. In some blood vessels, in fact, we can actually squeeze so tight that we can pinch the blood vessel entirely, stop blood from ever getting through. In other cases, we're just reducing the flow through. One other thing I'd like to highlight while we're here, vascular spasm is by far the most effective in one of our 5 main types of vessels. It's going to be most effective in arterioles. And here's why. If you remember the differences in the makeup of an artery and a vein, arteries have significantly thicker tunica medias, that middle muscle layer, than veins. They need to be able to expand and contract a lot more. So because they have a thicker tunica media, they can contract more. Arteries and arterioles both. But arteries are so wide, so thick, they're these multi-lane highways, you can't possibly close the entire thing, whereas arterioles are significantly smaller. So vascular spasm, very effective in arterioles, but it'll happen in all 4 of your blood vessel types: arteries, arterioles, venules, and veins. So there's our first step. Serotonin is released, we get vascular spasm. That's about all I want to talk about for that one. Now we're going to look at the secretion of this protein, von Willebrand factor, and we're also going to look at the role of platelets in this clot. Remember, platelets are a component of your blood. They form in that buffy coat. They're little, not even cells, we call them just granules. I'm going to draw a bunch of platelets in here. And platelets, one of the important features of platelets is that platelets love to stick to collagen. On our inside layer here, our tunica intima, we have endothelial cells. Cells have not collagen on the outside, but that phospholipid bilayer. So generally, in a healthy blood vessel, platelets will not stick to that. It's not collagen. But now that our other two layers are exposed, well, we've got collagen in both the tunica media and especially in the tunica externa. Platelets are going to find that collagen and start sticking to it on both sides. That's good. That's important. These endothelial cells are secreting von Willebrand factor, though, and that's going to cause a specific thing to happen to these platelets. It's going to change the membrane. Generally, the membrane of platelets is pretty smooth, but when von Willebrand factor is present, it's going to cause this cascade. We're not going to worry about all the nitty-gritty there. And it's going to change these from a smooth to almost a sticky. And the von Willebrand factor is hitting these platelets as well. And these platelets previously didn't really like to stick to each other. Now they're sticky on the outside, and platelets are going to be able to stick to one another because of the presence of this von Willebrand factor. So the platelets are going to start sticking to each other, aggregating, forming a big lump on both sides, and eventually that lump, I'm just going to draw circles again instead of squiggles, is going to fill all the way across and form what's called a platelet plug. So that's our second step. A platelet plug forms. It's not just the endothelial cells that secrete von Willebrand factor. Platelets actually have von Willebrand factor in self as well. And so it's going to create what's called a positive feedback loop. Von Willebrand factor is secreted onto these platelets. That's going to cause these platelets to secrete more von Willebrand factor. And so these are all secreting it, these are all secreting it, they're all turning sticky. It started with just a small amount of von Willebrand factor. Now we've got more and more and more and more, and these platelets are really, really adhesive at this point. So that's our second step. Von Willebrand factor leads to the formation of a platelet plug. It's important that platelets don't usually stick to each other in the blood. We only want them to stick to each other in the event of injury. If they could normally stick to each other, they're just going to form a big clot in your blood vessel, and we'll look later on the slides, that's very bad. That's the importance of von Willebrand factor. If you secrete it when you're not supposed to, you're prone to clots. If you can't secrete it when you're supposed to, it's going to lead to the inability to clot, which is also bad. Both of those extremes are bad. So we've got two steps so far. We've seen our vascular spasm, we've seen our platelet plug, and the last one is the most complicated, and that's going to involve this guy, tissue factor. Tissue factor is going to lead to one thing happening, which is going to lead to more things happening, a whole bunch of proteins interacting with each other. It's a very long pathway, and I'm not going to go into the steps of that. What I do want you to know is that pathway is called the coagulation cascade. Tissue factor interacts with one protein, which causes more proteins to change, Sometimes they're cutting, sometimes there's phosphorylation involved, but proteins are becoming active that previously weren't active. The final step in the coagulation cascade is the one that I am going to highlight, and that's going to lead to the formation of a protein called thrombin. So thrombin is a protein. It's going to be found all around here now because of our coagulation. Oh, he has a different color for thrombin. It's going to be found all around here because of, that's the same color I've been using. Because of our coagulation cascade, thrombin's present, and thrombin, its job is to act on a different protein found in our plasma. If we remember hearing about the protein fibrinogen, it's about to get involved here. Fibrinogen is found in the blood. I'm going to go ahead and make that orange. Running out of colors. Fibrinogen is going to be found in the blood, and I'm going to draw it with a shape sort of like this. Fibrinogen is in fact significantly smaller, but I just want to show you what's going on. We're almost done. Thrombin is going to cut fibrinogen into two different pieces. It's going to remove this part from this part. So thrombin is going to come in, act on this, separate fibrinogen into two separate pieces. One piece we don't care about, and one piece we care about a lot. This is the piece we don't care about. This piece is now a new protein called fibrin. And fibrin is super important. Fibrin, you can tell from the shape here I've sort of drawn, it's going to interact with other fibrins and form sort of a chain like this. I'm really bad at art. So this is going to be a fibrin chain. Or we would say that fibrin can polymerize. One fibrin molecule interacts with another and another and another and builds this big chain of fibrin. Fibrin in reality is much smaller than this. It's going to just form what looks like a long string. And these fibrins, once they're made, are going to get inside these platelets. You can think of the platelets forming this clot sort of as bricks. And now the fibrin is going to be the mortar that fills in this bricks, sews up all those tiny little holes. So we're going to get fibrin across here, and across here, and across here. And that's really going to sew this patch shut, when previously it was just a bunch of solid blobs. You can't form a clot without the fibrin and the platelets inside there together. So now, finally, our coagulation cascade has led to thrombin cutting fibrinogen into fibrin, and that has sewed our wound shut. Yes?
Can you explain fibrinogen with the thrombin?
Yes, so coagulation cascade, it starts with this protein tissue factor, and that's going to cause some stuff to happen, which causes some stuff to happen, that causes some stuff to happen. Finally, we get the creation, eventually, of a protein called thrombin. And thrombin is going to cause a certain reaction to happen. It's going to find that protein fibrinogen, and it's going to cleave that into two different chunks. One of the chunks we don't care about, that this guy, and one of the chunks is fibrin. We don't want fibrin just floating around in our bloodstream normally because we don't want it to polymerize and form these chains. You can see it's sort of got this ball on the top to stop it from polymerizing. It can't form a chain with this fibrin because that's blocking the way. Thrombin's going to cut this part off, allow that polymerization to happen. This whole string of arrows, by the way, is the coagulation cascade. So that's hemostasis. That's how a blood vessel repairs itself. Eventually, new cells are going to start growing over this patch, but it's important that as quickly as possible, we fill in that hole and stop the blood loss. This usually happens in a matter of like 3 to 6 minutes, start to finish, which by the body's time scale is actually quite slow. 3 to 6. If you missed that, yes, question.
Is this how the bruises form? Like, if the blood gets let out through the blood?
Yeah, so the formation of bruises, you're going to have your layer of skin way out here. There's several layers. Bruises are going to form when you break the blood vessel, but not the skin on top. Instead of the blood exiting your body, it just kind of fills in this space and this space. It's going to turn your skin that purplish, greenish, whatever color your bruise is colored.
Where does the blood go after that?
It chills in your body for a while, and eventually it's broken down and recycled into parts. Enzymes are going to come in and just start cutting things into smaller and smaller pieces. Okay, so that's our